Common ion effect is where you have chemistry that's going on and then you throw in something that's in common, an ion that's in common, and see what happens. And you should be able to predict using, especially if we're at equilibrium, you should be able to predict using Le Chatelier's principle how that concentration of the ion is going to impact that system that's in equilibrium. It's going to impact kind of the way that the reaction shifts. It's going to impact the side reactions that can potentially occur. When we're talking about solubility, the common ion effect has an impact on how much of something can dissolve. If I have extra of an ion around, right, if we're thinking about the dissolution of something into its component pieces, if I already have some of this ion around, or if I add something with one of these ions, then that's going to cause the reaction to shift more towards the reactants, right? You increase a product concentration that shifts towards the reactants, that'll cause more to precipitate out. So you can force a system to do this if that's what you're wanting. You want more precipitation, then maybe you want to push it in that direction in some way. Or if you don't want that to happen, then you can figure out the best solution that's going to cause maybe some of these ions to be removed, and that would shift the reaction in the other direction. So let's kind of talk about this in the context of barium fluoride. If we want to calculate the molar solubility, which would be the number of moles that we can dissolve per liter of barium fluoride in water, and again, we tend to measure these equilibrium constants at 25 degrees Celsius. We know that the temperature matters for equilibrium because a change in temperature can cause a change in the rate of the reactions, which is going to cause a change in the equilibrium potentially. That's kind of part of Le Chatelier's principle as well. So we're defining this as at 25 degrees Celsius. So for this particular reaction, the KSP is 1.0 times 10 to the negative sixth. Again, we're looking at a system that's not very soluble. It's barium fluoride is fairly insoluble in water under these conditions. So if we think about a quickie little ice box here, then again, I'm going to ignore this. It's a solid, so it's not going to be part of the equilibrium constant expression. When you first dissolve it, it's not going to have any of this. I'm going to have x here, 2x here, x, 2x. All right. So my expression for KSP is going to be equal to the barium ion concentration times my fluoride ion concentration squared. So if we plug in our numbers here, then my KSP was given, or lookupable, and that's equal to barium, which is my x, fluorine, which is my 2x squared. So now that's going to be 2 squared is 4, x squared is, x squared times x, so that gives me 4x cubed. So when I divide both sides by 4, then I end up with x cubed is equal to 2.5 It's 10 to the negative 7th. And you take the cube root of each of these guys, and you end up with an x is equal to 6.3 times 10 to the negative 3rd. Okay, so what was x again? X was my my concentration at equilibrium of my barium. I was asking about the molar solubility of barium fluoride. Since it's a 1-to-1 ratio, right, of barium to barium ions to barium fluoride, then that x is my molar solubility. It's how many moles I can dissolve of that per liter. Okay, you with me so far? All right, so that's, not very many. But what if I was to put it in a different solution? We said this was the molar solubility in water at 25 degrees Celsius. But what if I was to put it in a solution that had some sort of ion in common? So let's look at a problem like this. What's the molar solubility now of barium fluoride in 0.15 molar sodium fluoride at 25 degrees Celsius? All right, so here's where it kind of gets interesting, is the common ion that we have here, and I'll just kind of put this as a side note, is fluoride. So if I think about this system then, so we're still thinking about barium fluoride. So my icebox is going to be, you know, exactly the same in terms of setup, in terms of the reaction itself. But now the common ion is going to impact how much of this guy I start off with. If I have 0.15 moles of sodium fluoride per 1 liter of solution, then if I care about how much fluorine that is, then for every 1 mole of sodium fluoride, I have 1 mole of fluoride ions. So that means that I'm going to have a starting amount that's going to go here in my initial column, right? So if we have my icebox, ignore. We don't have any barium in this solution, right? We have some sodium floating around, but the sodium is essentially a spectator. I'm throwing barium fluoride into sodium fluoride, so there's already some fluoride in there, 0.15 molar specifically. And then we have the same molar change here, so we're adding X here, we're adding 2X here. So at equilibrium, I have X and 0.15 plus 2X. All right. Now this kind of changes my math a little bit when I'm thinking about this. My KSP value is the same, right? This was given in our first problem. So that's that 1.0 times 10 to the negative 6th. There's my KSP at 25 degrees Celsius. And that's now going to be equal to my X times my, 0.15 plus 2X squared. Now, one of the things that we've been able to do in the past is to ignore X if it's with within a certain distance of the KSP value and my concentration, right? Because if this is going to be small enough, if my X value is going to be small enough, then when I add it to 0.15, it's still going to round to 0.15. So I need to determine if this is negligible or not. And the way I do that is by comparing my KSP values to the concentration. If there's more than 1,000 times difference between the two, then I can assume that my X is negligible. So that's kind of nice because in this case it is. So we're going to disregard. Now I can't just disregard any X's. I'm disregarding this one with respect to the concentration because of significant figures and rounding. So now I have 0.15 squared with all my markings in here, sorry. Okay, so 0.15 squared times X is equal to this value. And so when I rearrange and kind of do my math here, then I end up with an X is equal to 4.4 times 10 to the negative 5. Okay, so what did I solve for again? What was I doing? Well, I was looking for the molar solubility of barium fluoride when I put it in a different solution. So this X value is the number of moles per liter of barium fluoride that I can get into this concentration of my sodium fluoride solution. And it's, again, it's a 1-to-1 ratio of the barium ions to barium fluoride, so we can just kind of do that. If it wasn't 1-to-1, then we'd have to do some rearrangement to account for the coefficients here, but this is just a handy way to do it. So this X value is the molar solubility. If we compare this to the value that we got in the first one, so here's my first problem. This was the molar solubility that we had in part 1. So this was in water. And this guy was in the sodium fluoride. Then we can see that the solubility decreased. And that makes sense because if I have it in sodium fluoride, then I have more fluoride ions present. So for this equilibrium, I'm increasing the concentration of my product, which should shift it towards my reactants. If I'm shifting towards my solid here, I'm precipitating out this solid, meaning that it is less soluble in that solution. And again, we see that with our numbers here, that in pure water, we have 6.3 times 10 to the negative 3rd moles per liter. But as soon as I put any of that fluoride ion in there, this concentration of sodium fluoride, which isn't really that concentrated, that 0.15 isn't that concentrated, then it makes a big difference on the molar solubility. So this is the common ion effect and kind of how it can impact our solubility and our KSP values.